Hello, everyone. Welcome to today's combustion webinar. And this is Peng Zhao from the University of Tennessee. And it's my great pleasure to introduce you today's speaker, Professor Li Qiao. And Professor Li Qiao is a professor in the School of Aeronautics and Astronautics at Purdue University. She also holds a courtesy appointment in the School of Mechanical Engineering. She earned bachelor and master degree in the engineering mechanics from Tsinghua University in 1999 and 2001, and also a PhD in aerospace engineering from the University of Michigan in 2007. Her research has focused on the development of new technologies and the understanding of basic science in the areas of fuels, combustion, and sustainable energy. She's a recipient of the NSF Career Award, AFOSR Young Investigator Award, and the Army Research Office Young Investigator Award. All the three you can imagine. And she's an associate fellow of AIAA and associate editor of AIAA Journal. She currently serves on the board of directors of the Combustion Institute. So with that, let's welcome Professor Qiao, and the podium is yours.
Well, thank you very much, Peng, for your kind introduction. I would like to thank the organizing committee for inviting me to give a webinar. I remember when the pandemic just started, March 2020, we were stuck at home. We couldn't go to conference, couldn't travel. And Professor Yi Guangzhu and Professor Wenqing Sun, they started this webinar. And then quickly we have organizer committee members from all over the world. And then every Saturday morning, 10 o'clock, and then we have a colleague in the community to share with us their research. So this has become something we look forward to during the pandemic on Saturday morning. Even though things gets better, the pandemic is not completely over yet, but I do appreciate this opportunity to connect with colleagues and to learn what other people are doing. So this is really great. So today I would like to talk with you about a few the work on Prechamber Turbulent jet ignition for combustion engines that my group and our collaborators have been doing in the past couple of years. Before that, I would like to acknowledge my graduate students who participated in this research. Dr. Sang-Yang Biswas, who is an assistant professor at University of Minnesota, Twin Cities right now, and Dong'en Li and Tian Xiaoyu are my current PhD student. The work is being sponsored by Caterpillar, Aramco, and Ford. Okay, all right. Please allow me 1 minute to brag about Purdue, which I am obligated to do so. The Maurice Zucrow Laboratory, the largest academic propulsion laboratory in the world, currently occupies a 24-acre site adjacent to Purdue Airport. So this is our airport. We do train lots of pilots and aviation technicians at Purdue. So the Zucrow Lab is basically operated by both the aeronautics and astronautic, as well as mechanical engineering schools. The facility has test cells with infrastructures that can perform real scale experiments that have attracted a lot of funding. As you see from these images, the topics covers a lot of different things, a wide range from compressors, high pressure combustion, to thermal sciences, fluid mechanics, in advanced laser diagnostics, to rotation detonation engines, rockets and gas turbine engines, and all the way to energetic materials. All right, so back to what I'm going to talk about today. I guess the first question is, many of the colleagues in the field, in the community have been talking about what's the future of combustion engines. There's no doubt that there is a energy transformation which is going on right now to address the challenge of global warming. We've seen renewable energy, wind, solar, geothermal, wave. They are basically emerging into the market that will help the community address the challenge and also create jobs. In terms of transportation, we have seen a trend. This is unavoidable. This is a trend that's going on, that is electrification. We see more and more electrical cars. That's why Tesla, stock price is rocket high right now. But we have to also honestly believe that IC engine will not disappear overnight. So they will still play a role in the global energy mix, at least for some time, a few decades. So here I'm showing you the data from US Energy Information Administration. So basically whatever scenario that a conventional gasoline engine will still occupy a certain market share by 2050. Right. And then there's also competition between hydrogen versus electric. And I don't know which one is going to win in the future. Most likely they will coexist, right? Electrical cars and obviously has a lot of advantages, efficiency and scalability, that's definitely. But hydrogen cars also have some hydrogen, derived from renewable sources like water electrolysis, also have a lot of advantages, and especially in those applications where the energy density requirement is higher. For hydrogen, there's also a competition between hydrogen combustion engine versus hydrogen fuel cell. Well, yes, fuel cell has a higher efficiency, perhaps maximum 52 versus 48 for hydrogen internal combustion engines. But fuel cell has a high requirement on fuel purity, right? Its tolerance to impurity is not that good. And also manufacturing at scale is a problem, the cost is high. So I guess my point is, nobody knows exactly what's going to happen in the future, although we can see the trend, but most likely these different energy technologies, low carbon technology will coexist, and also depending on the country's economic resources and situations may be different. So let me talk about what is Prechamber TJI. TJI means turbulent jet ignition. So here I'm going to play two movies so you can clearly see what is Prechamber turbulent jet ignition. So here you see this is a very typical spark plug that used in cars, right? So basically what happens, they generate a spark, a high temperature zone, which causes ignition and flame propagation. Now, pre-chamber ignition on the right. So basically, it's a device basically very, in terms of size configuration, very similar to a spark plug, except inside it, there's a hollow volume. Typically, this is a few cc, very small volume. And on top of it, there's a spark plug. So there's a spark plug inside it. Now, when this the mixture in the pre-chamber is ignited, pressure increases, and you see that there's small holes. These holes typically have diameter 1 millimeter or even smaller. So this causes high-speed jets coming out from these small nozzles, which, basic in the form of turbulent jet, which penetrates into the main chamber, cause ignition. So in this case, we have a pre-chamber, 4 nozzles, 4 jets that quickly penetrates into the main chamber, cause ignition and burning. The bottom is a simulation by my colleagues at Ramco, so you can clearly see the difference between spark ignition versus pre-chamber ignition. So you might ask, what are the benefits of TJI? Well, first of all, because For IC engines that either ultra lean or highly EGR dilution conditions, a challenge is how do we push the limit? Because when it's very lean or highly diluted, it's hard to ignite the mixture. Now, TJI has advantage because the ignition is not point ignition, rather it's distributed, it's multi-site, it's on the surface of these jets, which cause reliable ignition and also faster flame propagation and potentially lower cycle-to-cycle variation and mitigate knock. So the next question is, Prechamber TJI is not a new technology. It has been there for a few decades. What are the engines that use Prechamber TJI? I want to give you a couple of examples. Now, most Prechamber jet ignition engines are those very large bore natural gas engines for electricity generation, for mining, for power generation, for those. Those are basic stationary power generation. So here, this is example of Caterpillar G3600 series. It has 12 piston. The maximum power is almost 3,000 kilowatts. Now, all these stationary natural gas engine operates at very, very lean condition, okay? The fuel equivalence ratio can be as low as 0.5. So it's lean burn, which means we have a lot of excess air, which requires a very powerful compressor. Now, because it's lean burn, ultra lean burn, so there's typically no need for after treatment as the NOx level is very low. This is another example of GE Jambaka Type 4 stationary natural gas engine for maximum 1,500 kilowatts in power. Another category of engines that use Prechamber technology are super sports cars. Here is an image of the Maserati MC20 sports car, which easily costs $250,000 that I cannot afford. But these F1 technology-based sports cars use Prechamber technology. So basically in the cylinder, you see they have 6 to 12 jets coming from the Prechamber that penetrates into the main chamber for ignition and combustion. So here, Prechamber ignition for gasoline engines is new. Okay, so currently you see all the passenger cars on road, and none of them used Prechamber jet ignition. So this is still at very early stage, exploration stage for gasoline engine. But the good news is that one of the OEM is putting Prechamber in their cars. In a few years, we probably will see that passenger cars that use Prechamber jet ignition. So here I used the slides from my collaborator, Dr. Xingyu at Aramco. We have started collaborating 3 years ago. Aramco is a pioneer in Prechamber jet ignition technology. So here on the bottom left, you see this is a typical a turbocharged SI engine efficiency map from a passenger vehicle over here. So you see as a function of engine speed and BEMP, so indicating load, and then this is the brake thermal efficiency. Now so here, if you look at the very dark red area, that's the highest efficiency. But this dashed line below which we're going to run into dilution tolerance issue. And here, this is knock region. And then LSPI, that's low speed pre-ignition, which can take place at these extreme conditions. So there are a couple of challenges for us to further improve efficiency of gasoline engines, which include limited dilution tolerance at low and medium load, and knock at medium to high load, and LSPI at extreme conditions. So TJI can potentially help improve these challenges. As I mentioned earlier, because of the pattern of ignition, we can increase dilution tolerance. This includes both lean burn or high EGR dilution, and also mitigating knock because of fast and gas consumption and better target areas. Prechamber ignition have two types, passive and active. So here I have two pictures. The left one is a passive prechamber. It's kind of like just a spark plug, but with adapter. And then on the bottom, you see where you can design this to have different geometry, volume, and you have different number of nozzles, the diameter of nozzles, or location of the nozzles. But the gas goes into the prechamber, which is here, is by intake and stroke compression. So as the name suggests, it's passive. Okay. Now for active, which is on the right-hand side, it's an active prechamber, which means on top of here, you see this is the active injection line. Basically, we'll inject additional fuel into the prechamber. And we could also inject fuel air mixture. It depends. But basically, you have additional system to add more fuel or fuel air mixture into the prechamber. This is what we call active prechamber. And obviously, active prechamber will be more complex, but they give you some flexibility in terms of like manipulate the mixture in the prechamber to have the kind of combustion you would like to have. In general, prechamber volume is very small. It's between 1 to 5% clearance volume. For gasoline engines, it's around 1%. For the large bore natural gas engines, you could go as high as 5%. And then these nozzles are very small. Typically, the smallest I've seen is like 0.5 millimeter. And then the largest, these are for the large natural gas engine, they can be as large as 5 millimeter. Okay. In terms of number of nozzles, I've seen 4 nozzles, and the maximum that I've seen is 24. And then these nozzles, these tiny little holes, there's very interesting arrangement for optimization of aerodynamics. They're angled, they could be layered. Next, I'm going to share with you some of the results from my lab. So if you look at, fundamentally, you have hot jets, right, which are the combustion result from prechamber, now penetrates into a fresh, unburned, cold mixture, right? So this is basically a turbulent jet problem. So to better understand the fundamental mechanism of the jet ignition, we developed a single jet experiment. So here, basically, we designed a prechamber, and the volume is about 1% of the main chamber, and then there's a spark plug, and there's only one nozzle, which generates one single jet. And then because it's optical accessible, we can do visualization, high-speed imaging, quantitative measurement to understand how the properties of the jet correlates with the ignition outcome. First of all, I want to show you the ignition mechanisms. We test different prechamber designs, and then varying the orifice diameter, the nozzle diameter, and pressure temperature of the environment. And we found that there are 2 ignition mechanisms. The first one is called jet ignition. Basically, from the images, we can determine that the jets is basically a jet made of hot combustion products. There are minimum active radicals, OH radicals. And this basically means when, prechamber flame tried to pass through this tiny nozzle, less than 1 millimeter, it got quenched. So what's coming out is just a hot product jet. So let me play this simultaneous Shariran and OH chemiluminescence to show you. Let me play them together. So this is one single jet. This is the nozzle on the very top. Okay, they push some cold gas. Now this is the jet, right? The jet's coming out, and then ignition takes place over here and then expanded. Okay, I'm going to show you another, which we call flame ignition, because we found a lot of OH radicals when the jet's coming out. which means that when the flame passed through this tiny nozzle, it was survived. You still have the flame front with active radicals. So this perhaps a better illustration. So when the jet started coming out from the orifices, in the left case, we see appreciable OH signals. But on the right-hand side, there's no signal until sometime later. This is downstream here. Downstream of the jet, ignition started to happen and then propagate upward, downward, left and right, like expanding. And also from the pressure measurement we see for flame ignition that the main chamber pressure rise quickly, right? Because ignition, burning immediately took place. But for jet ignition, there's a considerable delay. That means the jets keep penetrating, and then after some time, perhaps when the environment, which is damp coolant number, is appropriate, and then ignition takes place, that we observe the pressure rise of main chamber like there's a delay. So this is essentially a fundamental problem. What happens when a flame tries to pass a small nozzle, right? A small channel orifice. This has been studied a lot in literature. We know when a flame trying to pass through a small channel, there's heat loss to walls. There could be radical quenching, and there's also highly stretched because these jet speed are very high, could be a few hundred meters per second. So these flame front are highly stretched, which can also cause extinction. So really the question is, the flame will be able to survive or quench depends on all these factors, right? Stretch rate, heat loss, radical quenching. Now, what we found was if we increase nozzle diameter and we observe more jet ignition, and that you can explain that, when flame try to pass a smaller or a smaller nozzle, there's higher stretch rate and high heat loss rate, which makes extinction more likely to happen. Another thing is that if we increase pressure, and we find that flame ignition tends to dominate. We tend to find more OH signals out of the jets, in the jets out of the pre-chamber. I guess you can use the quenching distance concept to explain it, because quenching distance decreases with pressure. So for the same diameter, whereas pressure increases, the flame able to survive had a better chance if pressure increases. I want to play a video that's just for fun because we observe when natural gas or hydrogen operates a very lean condition. In this case, the phi equal to 0.25 for hydrogen, that combustion instability start to show. You see the flame, the jet flame start to oscillate. And that's the instability at lean burn conditions that we will need to address. Next, I'm going to talk about our engine rig. So basically, our collaborators said, well, these single jet experiments very helpful. You have quantitative measurement that can help us to validate CFD or modeling result. But we really want something to be close to an engine, so that will be more helpful in terms of pre-chamber design and optimization. So we develop an engine rig. This is not really optical engine because let me see, sorry about that. So this is the whole setup is based on a GM 4-cylinder gasoline engine, but we only activate one cylinder, okay? And then we modified the cylinder. We installed optical windows from sides and the bottom so we can visualize the jet. We also fix the piston, so it's not moving piston, fixed piston, because we want focus on the jet penetration, the formation and ignition processes. So this is about the setup. I would like to show you a couple of movies to give you an idea, the jet process, which obviously depends on, how you design the pre-chamber. So again, because we don't have a dyno, this is a real engine configuration that the inlet exhaust valves are operated by electrical motor. So I want to show you the jet formation, penetration, ignition processes, and I'm going to use two pre-chambers. So the left one, as you can see, so this is the pre-chamber volume, okay? This is about 1.2% of the clearance volume. This pre-chamber has, on the bottom, you see it has 6 holes with a nozzle diameter 1 millimeter. Okay, the total area, so the total area basically means like the number of orifice, the number of nozzles times the area of each nozzle. Okay, the volume is about 1,210 cubic millimeter. This is the V/A ratio. Again, V/A ratio is a very important design parameter for pre-chamber optimization. So there are about a few cycles in the movie. So you see 6 jets coming out and then ignites the mixture and then keep burning the main charge. So this is the first cycle. As I said, there are multiple cycles. This is another cycle. You see one of the jets seems to ignite earlier than the other jets. A third cycle, again, these two jets seems to be more dominant than the others. Okay, this is the last cycle. And then on the bottom are the pressure history data, and you can see, each curve represents one cycle. There's some cycle-to-cycle variations, which I'll explain a little later. Now, next, I'm going to show you the jet processes for a different pre-chamber. So all the parameters are the same between these two. The only difference is that I have 10 nozzles. So you see there are 10 nozzles on the bottom of the pre-chamber. So the total area increased, volume and other parameters, including geometry of the pre-chamber, are the same. So see, that's 10 jets coming out, pretty uniform on this cycle. Another cycle comes in. You see, in this case, these two jets seems to be, occur later. A third cycle. All right, so with these visualization of the jets and measurement of pressure, so that help us to correlate the, the jet patterns with the main chamber combustion process, such as burn rate and cycle to cycle variation and so on. So from these videos, we observe, some cases, depending how many nozzles you have, ideally, if you say I design a pre-chamber with 6 nozzles, you would like to have, strong jets coming out of all 6 nozzles, right? And then quickly spreads, penetrates into the main chamber. But things is not always like that. So we observe that sometimes you have the jets more uniform, in terms of performance. Other times, like one or a few jets dominates, the other jets just disappeared. So here I want to give you an example. This is a pre-chamber with 4 nozzles. The first video is, where you're going to see the jets are more or less equally distributed. Oh, what's going on? Can you see the movie? No. Okay, it's coming. So this is what I call evenly distributed 4 jets. The 4 jets are more or less symmetric. Okay. All right. Let me show you the second one in the middle, where I, find it's unevenly distributed, which means some jets are igniting earlier than the other jets, and then they quickly penetrate and occupy the main chamber. Okay, can you see the middle movie? So it looks like the top and right one ignited the mixture earlier than the other 2 jets. Again. Okay, on the right-hand side, seems I'm having a little trouble with these videos, but nevertheless, on the right-hand side, you see 3 jets. That means there's 1 jet coming out, but then it's kind of died. This is on the far right. You see the 3 jets, top, bottom, left, but the right jet disappeared. Okay, so the question really is, what determines the number of jets that coming out from these nozzles, and what are the property of the jets? For sure, we know the property of the jets, such as the velocity, turbulent kinetic energy, and temperature, and dissipation rate. Those are all responsible for the outcome, which is ignition and flame propagation, right? But the question here is that ideally we would like to have as many jets as possible coming out, and then each of the jets would be able to ignite and then quickly consume the main charge. So what determines the number of jets? So we did some simulations using Converge. The conclusion is that the key factors are pre-chamber lambda and EGR distribution, okay? Which means the average lambda and EGR level are important, but the distributions are equally important, if not more. So I want to show you 2 cases. The top one are, the lambda distribution. Just pay attention to the pre-chamber, which is in the middle. Lambda temperature and also isotemperature contours. So the left 2 are a side view, and then on the right are bottom view. The top 3 videos are for a smaller nozzle, which has a diameter 1.2 millimeter, and the bottom one is a larger orifice, 1.4 millimeter. Okay, let me play this. Okay, hopefully you can see the movie. So you see the lambda distribution. Lambda is very, very high, which means lean, on this right side. That's why you don't see the jets coming out, right? You see the 3 jets on, from the bottom view, that's top, left, and right, down. But not the right jets, because the lambda near that orifice region is very lean. Okay, so it could not burn to cause a flame to propagate through that nozzle. Let me. Okay, now the bottom one, see if my mouse works. Okay, the bottom one looks like it's playing now, the movie. So again, you see that the jets start coming out from the right. In the left one, actually, we did not see a jet. Again, that's related to the local lambda in the nearby region of each nozzle. Okay. Now, next couple of slides, I want to share with you some of the engine testing result, which is very promising. I hope that you will get excited about these. Again, these results from my collaborator, Dr. Yu from Aramco. So they did a engine testing of pre-chambers. So basically, on the left side, you see that shows the chamber pressure and then different pressure between pre-chamber and main chamber for 3 orifices, 0.75 D, that's the 0.75 millimeter, that's the size of the nozzle. The 3 pre-chambers has 6, 8, and 10 holes, okay? And then the baseline is the spark ignition for comparison purposes. So if you look at the different pressure as well as apparent heat release profiles, for smaller nozzles, and obviously, I'm sorry about that. For smaller nozzles, the green line, you always see there's bigger delta P, right? Because the gas passes through smaller area that the velocity is. The velocity is higher, and then the pressure difference is higher. Now, in terms of the heat release rate, it's obvious all 3 pre-chambers have higher burn rate. The dashed brown line, which is the baseline. Okay, so TJI offers higher burn rate and reduced combustion variability, which is on the right-hand side. Again, this shows the combustion variability is about 3% for passive pre-chamber, whereas it about 5% for spark ignition at lambda below 1.6. Now, the bottom one shows the COV and NOx level for passive and active pre-chambers. One significant finding is that if you look at this bottom 3 curves, those are gases active pre-chamber. Basically, they injected methane as a fuel to the pre-chamber, okay, active pre-chamber. So this can push the lean limit, the lambda value from typically 1.7, 1.8 now to above 2, okay? So they can, TJI can improve the limit to above 2. And if you look at the NOx emission, it's less than 0.5 grams per kilowatt hours. This is another engine testing result. On the bottom left figure, summarize the engine platform and the ignition system. So the first 3 spark plug over here, and then the 2 green ones are passive pre-chamber and active pre-chamber. So just from this summary diagram, you can see the efficiency increased by 2.5% from the blue, and by another 6% from the light green using active pre-chambers. So again, from these maps testing passive and active pre-chambers, you can see knock limit extended using passive prechamber with externally cooled EGR, and then Lin limit extended between lambda equal 1.7 to 2 using gases. Here it's methane active prechambers. So these results are very promising. Basically, passive prechambers can achieve 13% increase in efficiency, and active prechambers can achieve about 20%, nearly 20%, use methane as a gaseous active prechamber using ultra-lean combustion. All right. So I've described some promising engine testing results of both active and passive prechambers. Next, I want to talk about challenges of simulating prechamber ignition engines. We often hear from our collaborators and colleagues in industry, many of them use converged simulations. It's hard to match engine testing results with simulations, and this has caused us to really think about, when you add a prechamber to a gasoline engine or a large bore natural gas engine, what really happens to the combustion mode? So here I have the famous Bogie-Peters diagram. I know everybody is very familiar with this. This diagram is in log-log form. So you see the whole area is divided into different zones, because the physics are different in terms of the combustion mode. For example, lambda flames, and then on the right-hand side, wrinkled flames, corrugated flamelet. So here is basically, flamelet. And then all the way to second wrinkled flame, second flame, and then eventually thick flame. This is the region we used to call broken reaction zone. Anyway, you can see for SI, spark ignition operation, it's here. This is the brown area. So mostly the condition falls into corrugated flamelet zone. Now with dilution, which could be air dilution, which means lean or ultra lean operation, you see this blue curve. And also with EGR dilution, the black curve. So basically the mode moves from corrugated flamelet zone to second wrinkle flame, okay? Now, when we simulate prechamber ignition engines, we have to consider two additional processes. One is the combustion process in the prechamber, right? The other is, when the jet's coming out, right, it quickly ignites, and then it's a turbulent jet combustion. We have to consider those two. So I want to show you where those two processes fall into in the Bogie diagram. So this is where the prechamber combustion, it has overlap with SI operation, but more significantly is the turbulent jet combustion. So for gasoline engines, it most likely into two regimes, thickened, wrinkled flames, as well as second flames. For natural gas engines, because of the much higher operating pressure, it's very likely that those jet combustion may fall into the thick flame zone. So I hope by this you're clear about the challenges of simulating, which turbulent combustion model are you going to use, because you have different processes within the same engine that falls into different zones, right? Can we use flamelet model? Well, if the jet combustion is in a thick flame zone, that's not going to be accurate, right? And some use sage models that really not good enough, I would say, for highly turbulent jet combustion, unless, parameters needs to be tuned. Okay, all right, this is my last slide. I would like to share with you, In terms of pre-chamber jet ignition, we found there are two ignition mechanisms. If you ask me, do you know an engine, which mechanism, for gasoline engine or for natural gas engine? My answer is no, because it depends on your design of the pre-chamber, like how many nozzles, the size of the nozzle, and then the operating temperature and pressure and so on. But one thing is for sure is that in terms of turbulent kinetic energy, the jet contains much, much higher turbulent kinetic energy than the flow in the pre-chamber and then the flow in the main chamber. And these kinetic energies self-induced, okay? And because of that, the jet ignition combustion, when the jet comes out, that process may fall into the thick flame zone or thickened flame zone. However, most combustion devices operate in the thin reaction zone. So this makes monitoring these processes very challenging. Now, engine testing results have given very promising result. I have reported to you, pre-chamber TJI can increase dilution tolerance and also mitigate knock due to fast end gas consumption. Engine testing show the efficiency can be increased by 13% for passive pre-chamber and nearly 20% for active pre-chambers. At the same time, we have to understand there are several challenges of pre-chamber technologies. For passive pre-chamber, unstable combustion, misfire, a low load condition could be an issue. And also passive pre-chamber has very limited LIN or EGR dilution tolerance. Now, active pre-chamber can, better tolerate LIN burn or EGR dilution, as I showed earlier, but it requires a booster system, right? It's more complex, it adds more cost to the manufacturing process. And if you want to use gasoline as the additional fueling process, that means inside such a small volume, a few cc, you need to break up gasoline and vaporize gasoline. The whole process is just very difficult, very challenging. If you use gases, say as methane, that's easier, but again, you're going to have a different fuel system on board. It also may require LIN after treatment. Okay, all right, that's my last slide. Thank you for your attention. I'll be happy to answer your questions.